Hi. So in today's lecture, we are going to kind of do the opposite of what we have been doing till now. So until now in the course, we have looked at various techniques to design approximation algorithms for problems. Yeah, and these problems were NP hard to compute exactly, which is why we had to resort to designing approximation algorithms for them. Now what we are going to do is flip over to the other side and say that, look, unless something really bad happens, we cannot hope to give good approximation algorithms for these problems. By good, I mean uh, we cannot hope to approximate the optimal solutions to these problems in the worst case to better than some factor alpha. Now, as I'd mentioned towards the end of the last lecture, this is an entire field in itself, and we'll just start off uh, a small discussion as to how these things are done. In particular, what we're going to start off with is the framework in which we can frame these problems. That is, how do you show that a problem is hard to even approximate? Okay, so for that, we'll need to define what are gap preserving reductions. And then I will state a version of the Pcp theorem, where Pcp stands for probabilistically checkable proofs. Now, this version by itself will not involve proofs or checking at all, but we'll come to the proof checking version of it in the next lecture. Okay. Now, this was one of this theorem was one of the major breakthroughs that happened. It happened in the early 90s, and using it, a number of hardness of approximation results were proven. So what we'll do is use this PCP theorem to show certain hardness results for the max clique problem and the min vertex cover problem. Okay, and if time permits, I will start with the proof checking view that will continue into in the next lecture, and I'll give you more details about it then. Now, the way I start this off is going to sound very familiar to you, and it might remind you of the first lecture in the course. Okay. So I'm going to start off with asking, what is the class P? So roughly speaking and informally, P is the set of problems which have polynomial time algorithms. Okay, so examples of this are, say, the min cut problem, the max matching problem, and so on and so forth. All the problems that you might have seen in an undergraduate course on algorithms. The class NP, if you recall, it is not polytime. So it actually stands for non-deterministic polynomial time. Okay. So these are classes of problems, as you've seen through the course, where you can actually provide a certificate that says that the problem, a certificate that can be verified by a verifier running in polynomial time. So for example, if you take the CSAT problem, the certificate is an assignment to the variables. If you take the 3 coloring problem, the certificate is a coloring of the vertices of G, and so on and so forth. So if someone came around and asked you, is this graph 3 colorable? Well, you can't really answer that in polynomial time. However, if someone gives you a coloring, you can verify whether that coloring is valid or not for the graph. And if it has just 3 colors, if it uses just 3 colors and is valid, you can say that the graph is 3 colorable. Okay. So informally, NP corresponds to those problems in which you can verify a certificate of correctness in polytime. And at the same time, if someone gives you a wrong certificate, for instance, if they give you a certificate that is not valid in terms of 3 coloring, suppose they give you a coloring that is not um, that uses say 4 colors, or it colors an edge, both endpoints of an edge the same color, then it's not a valid coloring for the graph. They should be able to reject such certificates. Now, if you recall, in both of these classes per se correspond to languages or decision problems. So these are all the class of decision problems. So even though I stated min, cut, and max matching, etc., ideally the question, the decision problem that you're asking is given a graph G, is there a matching of size K? Okay, so this is the kind of question that you're asking when you frame your max matching problem as a decision problem. If you recall, NP-hard problems corresponded to the hardest problems in NP. Okay, so example, so suppose you take the 3-SAT problem. You can reduce any problem to 3-SAT, any NP problem to 3-SAT, and this is the famous Cook-Levin theorem. Okay, and by reduce, I mean that if you can solve 3-SAT, then you can solve the given problem. Okay, so 3-SAT is one of the hardest problems in NP, and various other problems using such reductions were shown to be NP hard. Okay. Now, while it is easy to say that, easy to see that P is a subset of NP, the big question is whether P is a proper subset of NP. That is, are there problems in NP that are not in polytime? And a simple candidate for these problems, of course, is the class of NP hard problems, okay, that are also in NP. So it is widely believed, or at least people would like to believe, although there's no proof of this fact, that P not equal to NP. So what this implies is that NP hard problems don't have polytime algorithms. Yeah, and this is a central open question in computer science. But people believe it so much that it's a very safe assumption to make when showing any sort of results. Now, suppose pi is a yes no problem. Okay, that is, it is a decision problem, and I kind of think that pi is NP hard. How do I go about showing it? Well, you pick your favorite NP hard problem. Let us say I take 3-SAT. Okay, now 3-SAT has got two kinds of instances. Okay, the formulae phi that are satisfiable and those that are not satisfiable. So yes instances are those that are satisfiable and no's are the unsatisfiable. Okay, and here's my problem pi, okay, which again has both yes and no instances. Now the way to show that pi is NP hard is to produce a reduction from 3-SAT to pi. That is, produce a mapping that takes in a SAT instance or a 3-SAT instance, and it should spit out an instance of your problem pi. Okay, and now this reduction should run in polynomial time. And secondly, f should satisfy the following, that if your 3-sat instance was a yes instance, that is if your formula phi was satisfiable, it will take it to a satisfiable instance I of pi. Okay, and if this was not satisfiable, it will take it to a no instance of I of pi. Okay. Now, the important thing to remember over here, that f itself being a polynomial time procedure is not going to be able to say if the 3-sat instance that it receives over here, if this 3-sat instance is actually satisfiable or not. Okay, so it will run oblivious to the fact of whether phi is satisfiable or not. It will just take in some phi, output an instance I, and we need to prove that the property of f is such that if phi is satisfiable, I is satisfiable, and the other way. Now, this immediately tells us that if pi has polynomial time algorithms to decide whether the instances are yes or no, then 3-sat has polynomial time algorithms, because this map is preserving yes, no, and hence if both of these are satisfied, if you find such a mapping, then you will say unless p equal to np, pi has no polytime algorithms. Okay, so this is the conclusion that you would draw. Now, how do you show NP hardness of approximation? Well, you need to adapt this language a bit to include approximability. And we do that by introducing the concept of gap preserving reductions or gap creating reductions. For that, we need the notion of what is a gap problem. So gap problems are basically the yes-no equivalents of optimization problems. So for example, suppose you take the max 3-sat problem. Okay, so you want to find an assignment that maximizes the number or fraction of satisfied clauses. So if you have the corresponding gap version, is just going to ask you, is there a gap between the number that can be satisfied in one case and the other? So the gap version of this I'm going to call, and it will have two parameters, 1, alpha, max 3-sat. This is a yes-no problem, which given an input phi, the yes instances are those which are completely satisfiable. That is, there's an assignment that satisfies all m clauses, and the no instance is if the maximum number of satisfiable clauses by any assignment is less than equal to alpha times m. Okay, where m is the number of clauses. Okay, that is, any assignment can satisfy at most alpha m clauses. So notice that according to this definition, there are a whole bunch of formulae phi which fall in neither of the yes or no classes of this problem. Okay, and that is why it is called a gap problem. So the way you visualize this is the following. You have some instances, the yes instances over here, opt, which is the maximum number of satisfied clauses by any given assignment, is equal to m. Then you have a gap where you don't specify anything about these clauses, and the no instances are those where opt is less than equal to alpha times m. So when you look at such a gap problem, which does not specify whether certain instances phi fall in the yes or no class, these are called as promise problems. Okay, that is, the given input really matters only if it falls in the yes or no class. Again, you don't care about the inputs that fall in this intermediate class in between, which is undefined. So the inputs to the gap 1 alpha max C set problems will only fall, are given to be either fully satisfiable or less than alpha m satisfiable. Now, this is a yes no problem. And how do you show that the gap alpha problem is hard? Well, you're going to show a reduction from C set. Okay. That is, you want to produce a polynomial time mapping, okay, that takes the 3-sat instances as input, and the yes instances is going to map to the yes instances of gap 1 alpha max 3-sat, and the no instances are going to be mapped to the no instances over here. Again, f should follow polynomial time procedures, and it should preserve yes no instances. And as you have seen before, or you might be familiar with, that your starting problem here can be any NP hard yes no problem. It need not be 3-sat. Manage to do this implies gap 1 alpha max 3-sat is NP hard. Okay, cool. So we have set up this, and you might ask, why am I looking at such gap problems? Okay, the reason is that showing hardness of gap problems immediately implies hardness of approximation ratio. And let's see why that is true. I claim that if gap 1 alpha max C-sat is NP hard, then no polynomial time algorithm can actually give you an alpha approximation for max C-sat. So let's see why that is true. This is quite simple to see. Suppose A was a alpha approximation for max C-sat, right? Then what do you know? Well, I'm going to take a C-sat instance, use the mapping F because I know such a mapping exists, right? Use the mapping F to produce a gap 1 alpha max C-sat instance. Okay. Now, if it's the yes instance, then what is the value that you would get? Well, you would get an alpha approximation. And because it is satisfiable, you're going to kind of end up with an assignment that satisfies at least alpha m clauses, right? Because it's an alpha approximation. But let me change this to opt strictly less than alpha m over here. And now notice that whatever A does on a no instance, it cannot get alpha m clauses satisfied because the no instance by definition have opt less than alpha m. Okay. So this implies that the no instances can get at most alpha m minus 1 clause is satisfied. So basically you can use the algorithm A to differentiate between the yes and no instances of gap 1 alpha max CSAT, which by this chain of reduction means that you can differentiate between the yes and no instances of just the decision tree SAT version. Yeah, and this is not possible. Yeah, is what is assumed, assuming P not equal to N. So clearly I need to augment the claim that this assumes P not equal to NP. Okay. So just generalizing this above kind of reduction, what we'll have is usually say 3-sat, or for that instance any other NP hard problem, and we are going to produce such a reduction F which maps it to our instances of problem pi, where the S instances have opt say greater than alpha, the max instance, the max problem, and here you have opt less than beta. Okay, and if you can find such a map F that does this, that maps the yes instances over here and the no instances here and never produces the instances of this form, this implies that the problem pi in its optimization version is NP hard to approximate to within a factor of alpha over beta, or rather say beta over alpha. Okay, beta is less than alpha, it's a maximization problem. So for instance, in the case of gap 1 alpha max 3-sat, this alpha over here was equal to m, and here it was equal to some epsilon times m, beta was equal. And such a reduction is called a gap introducing reduction, because you're kind of introducing a gap from pure yes no instances of 3-sat into this alpha versus beta gap instance. Now, like you'd have seen for just NP hardness reductions, it's actually a little difficult to keep going back and starting from 3-sat at every point. So once you show that some problem is NP hard, you can use it to further show that other problems are NP hard. So now, suppose I know that a problem pi in the gap version is NP hard, okay, and I manage to transform this using a polynomial time reduction to some other gap problems, which is, let me call this gamma, with opt greater than alpha prime, beta prime as the yes no instances, such that F maps from pi to gamma by preserving the yes no instances. Notice that you're not guaranteeing anything on what F does on the intermediate instances when the opt of the pi instance is between alpha and beta. Then using this, you will say that gap alpha beta pi is NP hard would imply that gap alpha prime beta prime of gamma is NP hard. Okay, which would also mean, as you have seen, that gamma is NP hard to approximate within a factor of beta prime over alpha prime. So I'm always talking about maximization problems. You can also make the same thing about minimization problems, where your yes instances in the minimization problems will be opt less than some alpha double prime, and the no instances will be opt greater than beta double prime. For instance, you can have a min vertex cover problem where the yes instance is that the min vertex cover is of size less than k, and the no instances is that all vertex cover are of size greater than 2k. So what we have actually argued is that there is actually reduction all the way from 3-sat to the problem gamma by just composing the reductions from 3-sat to pi and then from pi to gamma. which is quite cool. And like in the NP hardness case, once we prove that some problem in its gap version is NP hard, it will be much easier for us to use the gap versions of problems and reduce those to gap versions of problems that we want to show are NP hard. So such reductions over here, which preserve the gaps, are called gap preserving reductions. It is not necessary that the alpha and alpha primes should match up, or the beta and beta prime should match up, or for that matter that alpha by beta and alpha prime by beta prime should match up. However, as long as the gap is preserved, we'll call it a gap preserving reduction. Now, while the theory of proving that a problem is NP hard was developed starting with Cook-Levin's Cook-Levin and Karp's proofs, it was actually a major open question until the 90s whether, for instance, vertex cover has a p-TUS, or whether even clique has a p-TUS, and so on. Okay, max clique and min vertex cover. And the reason that this was prevalent, that people did not know the answers to these questions, was basically that we did not have a gap problem to start off with. Okay, we had our original CSAT that was NP hard, but it was not possible to show any meaningful gap between the yes and no instances of CSAT. That anything from the yes and no instance of CSAT, you can have a gap introducing reduction from that to either of these problems. Okay. And this changed with the advent of the Pcp theorem, which was proven in 92 by Arora, Lun, Motwani, Sudan, and Segedi, and also Arora and Safra. Which basically did effectively the first gap introducing reduction. Okay. And what this said was gap 1 comma 1 minus epsilon naught max CSAT is NP hard for some constant epsilon naught greater than 0. Okay. So effectively it showed the following gap introducing reduction. So you have opt equal to 1, or opt equal to m, and opt less than equal to 1 minus epsilon naught times. Okay, and this was again the max CSAT problem. Okay. Now if you look at the theorem itself, epsilon naught would have turned out to be something like 0.99999, some really small constant of this form. Okay, some really large or close to one constant of this form. And so you might think after a bit of thought that this might not be really useful, because notice that as the gap between the yes and the no instances here rise, you really the problem to distinguish between them intuitively becomes simpler. Okay. So to distinguish between an instance of phi which is completely satisfiable versus one which is really small satisfiable is really difficult. Should be much easier. Okay, so let me just, that was a slight mistake in what I said. What I mean is epsilon was a really tiny number. Okay. So what I mean is that the yes and no instances over here had a really small gap. But this itself is still a constant fraction gap, and that was the main thing. Okay, so what you're looking at is differentiating between max CSAT instances which are which are completely satisfiable versus those that are 0.9999 m satisfiable. Now this gap introducing reduction was the starting point of showing various other hardness of approximation results. And we'll see how in the later part of today's lecture as to how you can actually, assuming this PCP theorem, actually show that min vertex cover does not have a p-test and max clique actually cannot be approximated to any constant factor. So you might ask, what is the meaning of PCP over here? PCP stands for probabilistically checkable proofs. Now this whole term needs some explanation, and I will give you a more detailed explanation in the next class, okay, and how it proven. Suffice to say that the idea of using checkable proofs developed independent of the quest initially of showing hardness of approximation ratios. Okay. And only later, once the theory was developed, it was more as started as a way to investigate uh, the nature of NP hardness in some way. And only afterwards was it realized, once the theorem was developed, it was not in the form as I've written it currently, that it can be used to show hardness of approximation results. Now, a quick idea of why you would think of checking proofs and all is the following. You can always view an NP problem as I said, you need to verify a certificate in polynomial time. So here's a verifier who knows, say, a problem P, and given a proof, which is in this case, if phi is a 3-sat formula, a natural proof is to ask for an assignment of values to the variables. So the verifier goes over this proof, substitutes the assignments um, into the formula, and sees whether all the clauses are satisfiable or not. Now, what does a probabilistically checkable proof means? It means that the verifier need not look at the entire proof for an NP-hard problem or for a problem in NP. Rather, the proof can be written in a different format, okay, such that they verify randomly, and this is where the probabilistically word comes in, randomly query some locations of the proof and then can decide with some probability whether the formula phi is satisfiable or not. And this characterization of NP is what is maybe at this point rather surprisingly related to the theorem that I've written above. Okay, so what we're going to do next is to see a couple of reductions. Okay. The first we'll see will be a gap introducing reduction that will show hardness of the non-metric version of the traveling salesman problem. Okay. And next we'll see a gap preserving reduction that is going to use the PCP theorem I just stated in order to show hardness of min vertex cover and max clique. So let's start with the gap introducing reduction. So I claim, and the theorem is that non-metric TSP is NP hard, or rather let me state it this way, non-metric TSP does not have a alpha n approximation algorithm that is polytime unless p equal to np for any alpha n which is polynomial computable. Here n is the number of vertices or number of points in the TSP instance. Now, how does one go about showing this? To go back to the language that you have used earlier, we are going to show a reduction from NP-hard problem, which is a yes-no instance. We're going to show a polytime reduction such that the yes instance is there. Notice that TSP is a minimization problem. You want to minimize the length of the tour on all the vertices. So the yes instances will map to instances over here, TSP instances that have a tour of length at most say n, and the no instances will map to tours of length greater than alpha n, where alpha n can be as large as you want as long as it is polynomial time computable. Now, what is the starting problem going to be here? It's not going to be 3-sat, rather it's going to be the Hamiltonian cycle problem. If you recall, the input to the Hamiltonian cycle problem you're given a graph on n vertices and you want to check, is there a cycle that goes through all the vertices? So for instance, this graph does have a Hamiltonian cycle, which is just the square outside. Okay. Now, how do I map this to an instance of the TSP problem? Well, the mapping is as follows. Given a Hamiltonian cycle path problem, now I should say that this is NP hard to decide given a graph if it does have a Hamiltonian cycle or not. Okay. And because this is NP hard, what we'll do next is, given an instance of the Hamiltonian cycle problem, I'm going to produce an instance of the TSP problem, which is a set of points and a distance function between them. Now, how am I going to define the distances? X is going to be my vertex set, or there's going to be a direct map correspondence between the points in X and the vertices in G. So I can identify them. And the distance between any two points in X is going to be 1 if ij is an edge in the graph, and it is going to be something like alpha n. Maybe I'll have opt greater than alpha n plus 1. If ij is not an edge, then the distance in this metric in the space is really large. Notice that this need not be a metric. Okay. So now what do I need to show? I need to show that if G has a Hamiltonian cycle, then what does it mean? I want to show that there's a tour of all the points which has distance at most n, okay, which has cost at most n, and this is simple. Because you just take the same edges. Okay, so if G had a Hamiltonian cycle, you just follow that order even in the TSP instance, and you will get a tour of cost n. Okay, so this is exactly equal to n. And if G does not have a Hamiltonian cycle, then what this means is, if you look at any tour in this that crosses all the points, the tour has to take a non-edge. So the distance on this is at least alpha of n times n plus 1. That means the total distance of covered by the tour is greater than equal to alpha n times n plus 1 plus n minus 1 or something, which is greater than or equal to alpha n. Okay. So now what this has given us is basically the fact that the S instances map to small 2's and the no instances in the Hamiltonian circle problem map to really large 2's. Okay, and therefore this proves the theorem that we wanted before, because it showed that the gap version of the non-metric TSP is hard. Notice that here it is crucial that the distances here do not form a metric. Okay, so you can have say 3 points I, j and k, but the distance between I and k is really large. It's something like alpha n, whereas because these were edges in the graph, I, j and jk have got distance at least exactly 1 from each other. Now in the original, what we had seen in class before was a 3/2 approximation, but that was for the metric TSP. Now, if you want this to be a metric, you'll find that alpha n has to be as small as 1 over n. Okay, of the order of 1 over n for to be a metric, and the corresponding hardness of approximation that you get is going to be a gap between something like 1 and 1 plus 1 over n, which is hardly anything. Okay, so it does not really give a meaningful hardness of approximation result for the metric version of TSP. So let's go on to the second reduction I want to show you, this time a gap preserving one, which will show hardness of the clique problem. Now the starting point of our reductions, as I said, will be the fact that a gap version of the max CSAT problem is NP hard. That means it is NP hard to differentiate whether a 3-sat instance is completely satisfiable or at most a 1 minus epsilon naught fraction of the clauses is satisfiable. Okay, and here I've just switched notation, and instead of using m and 1 minus epsilon naught m, I've only denoted the fraction here in the gap. Now, a small note about gap problems, maybe it's best to clarify it here. Um, so suppose I have to differentiate between instances of gap problems with opt greater than alpha and opt less than beta. So there's a huge gap here. You just want to say an algorithm that says yes to instances if they come from this class and no if they come from this. Notice that if I shrink alpha and beta towards the ends, so if you have alpha prime greater than alpha and beta prime less than beta, and you want to say yes and no, then this algorithmically is a much easier problem, okay? Or it is a easier problem. Now, if you look at it from the point of view of proving hardness results, then showing a hardness result for a larger gap is more difficult. Because algorithmically the problem gets easier, it is harder, or say it requires more effort to show that gap, say alpha prime, beta prime, NP hard. Okay, so maybe harder will replace with needs more effort. So I'll just state this and leave it here. for reference later. Now let's come to the problems that we want to show are hard. We want to show that max clique is hard. Okay. So what we'll do is show that some gap a comma b clique or gap a comma b max clique is hard, and we'll show that gap some c comma d min vertex cover is hard. And we'll show this by using a gap preserving reduction from our given SAT instance, or by using the uh, Pcp theorem. So let's start with the SAT instance. Now the first observation that I'm going to state is that max clique is the same as maximum independent set in terms of solutions. Okay, so this is because suppose I call a clique in G is exactly an independent set in G complement. Okay, so G complement is the complement of the graph G, which means there are edges between every pair that did not have an edge in G and vice versa. And this is easy to convince yourself of. So what we'll in fact show is that gap AB max independent set is hard. Okay, and we'll show for some constants A and B. So we'll figure out what these constants are once we have defined our polytime reduction. Let's start with, if you remember the picture, we're going to go from this CSAT instances, which are 1 versus 1 minus epsilon not satisfiable, to our independent set instances. And what kind of instances will these be? These will have alpha of g greater than equal to something. Again, this independent set is also a max problem, so the S instances will go here, and you'll have alpha of g less than equal. So from a formula phi, we need to come up with a graph G, and the way we do that is the following. So phi consists of some m clauses, right? So suppose I take a clause Cj and it was equal to say x1 or x2 or x3 bar. I'm going to add 3 vertices in G phi and connect all of them. They will correspond to x1, x2 and x3 bar. Okay. Now suppose I had another clause Pj prime, which was say x2 or x5, or let me say x2 bar or x5 or x1. Then again I would have 3 vertices. Though x1 is repeated over here, I'll still have another vertex. I won't label it x1, I will label it rather x1 j prime, which is the occurrence of x1 in the clause j. This is the occurrence in j of all of these. Then you have x2 bar and x5. Okay. And now because x2 occurs over here as a positive literal and here as a complemented literal, I'm going to add an edge between these two. Okay, so I add edge between two literals occurring in different clauses, their corresponding vertices in the graph G phi, if one of them is a complement of the other. Okay, so if I had a third clause like ck to be equal to x1 or x1 bar or x3 or x7, then I would have another triangle with x1 bar, x3, x7 for ck, and the x1 here would connect to x1 bar and x1 connect over here. Okay. You will not have an edge between two x1s that occurs in different clauses. Okay, so this is kind of the standard reduction to maximum independent set, and I claim first of all that if opt of phi is equal to m implies the size of the maximum independent set in G phi is equal to m. In fact, I'm going to make a stronger claim that will cover both the yes and the no cases. I'm going to say that opt of phi, the size of the largest independent set in G phi. Now the proof of this is quite easy, and I will just leave it as an exercise, the details. The idea is simply that if you choose a satisfying assignment, okay, if opt of phi, if phi had a satisfying assignment, then within each clause you could choose to one vertex that is set to 1. Okay. Or more generally, choose any one vertex whose literal is set in the optimal assignment phi. And you'll choose one per every clause. Okay, and you will always be able to do this while maintaining an independent set. Okay, and conversely, if you have an independent set in G phi, you can translate it back to a valid assignment for phi. Okay, so I'll leave the details here. And notice what this gives us immediately. This tells us that immediately you have a gap preserving reduction that maps CSAT instances to maximum independent set instances. In fact, if you have gap 1 comma 1 minus epsilon naught, again gap of 1 comma 1 epsilon naught is the number of vertices. And because you have translated the yes and no instances this way, this means that there's a gap preserving reduction. And because by the PCP theorem, your starting point, that is gap 1 minus 1 comma 1 minus epsilon naught of CSAT was NP hard, the corresponding gap max independent set problem is also NP hard. Okay, which means that it is NP hard to approximate the max independent set to within this factor of 1 divided by 1 minus epsilon naught. Further, because of the equivalence between the max independent set problem and the max clique problem, the hardness results also transfers over. Okay. Means that gap of, well, here the 1 and 1 minus epsilon naught is actually a fraction of the number of vertices. So, oops. I should say 1/3 1 minus epsilon naught by 3. Okay, I've been a little loose over here when I'm using fractions. What I mean is that to distinguish between on an n vertex graph, if n over 3 plus 1 minus epsilon naught n over 3 is the max clique of size n over 3 or less than 1 minus epsilon naught n over 3, be hard. Okay, the same result holds for independent set also. So let me now go on to min vertex cover, and actually the reduction is exactly the same. It is not hard to see that the maximum independent set and the minimum vertex cover in any graph are related by an additive factor. So I'm going to let beta of G phi denote the size of the minimum vertex cover. G phi, and for any graph we know that the minimum vertex cover is size of vertices minus max independent set, which I've called already as alpha of G. Okay, this implies that, oops, sorry, beta of G P is equal to m minus alpha of G phi when you reduce from an instance. So what does that mean? We are going to use the same, that is, we are using the same transformation for phi to an instance as we did before, except that now the analysis is for the min vertex cover in that graph G phi. Okay. So if opt of phi is equal to m, that is it is perfectly satisfiable. This implies that the size of the minimum vertex cover is equal to 3m minus m, which is 2m. Okay, and if opt of phi is less than equal to 1 minus epsilon naught times m, this implies that beta be equal to 3m minus, well, you have the same number as being the size of the min vertex cover, the size of the maximum independent set times m. Okay, and if you change this, this is nothing but, sorry, this inequality should go the other way around, and this is greater than, I can put 2m over here, which is 2 plus not m. So this means that gap of 2m comma, or rather I should say 2 plus epsilon naught m of min vertex cover is NP hard. This is NP hard. It's NP hard to decide if the min vertex cover is of size less than 2m, which is the yes instance, or it's greater than equal to 2 plus epsilon naught times m. This implies that NP hard to approximate min vertex cover to a factor of 2 plus epsilon naught by 2 is 1 by 2, which is some constant greater than 1. So notice that using the PCP theorem, we have managed to show constant factor gaps for both clique and min vertex cover. Okay, and the remarkable fact about the PCP theorem is that it introduced a gap between yes and no instances of the max CSAT problem. So I'm going to stop here. What we are going to do next time is look at how to amplify these gaps to get stronger hardness of approximation results, and also look at the proof checking view and introduce the label cover and the unique games problem that I've talked about for some time in the previous lectures. Okay, so I'll stop here. That's all for the day.